Right. Ahluwalia sir is there?
Yeah, I'm there.
Yes, sir.
It's a matter of great happiness that we are having today Vijay Singh as our speaker for this series on physics education research.
Yeah.
And it's a matter of pride for us that Professor Vijay Singh has steered IAPT as the president of IAPT itself.
Excuse me, Ahluwalia sir, please आपका वीडियो बंद है, वीडियो चालू करें.
Okay, is it okay now?
Yes.
Yeah. So
Yes,
thank you very much, sir, for gracing this occasion. I also welcome Professor Yogesh Vijayji to kindly be present here and preside over this particular lecture. We are happy that we have very distinguished persons today with us. Professor Ajay Ghatak also is with us. Professor Deshmukh, I can see, is here. And there are very many senior members of IAPT and of physics community who are present in today's lecture. I really liked the topic of today's talk, whether it is something which is very interesting. I think this could have come from Professor Vijay Singh only, whether we can really make a comparison between whether it is an art or a science. I think we are very eagerly looking forward to your lecture, sir. Once again, I welcome you and welcome all the participants. Thank you very much.
Thank you, Professor Ahluwalia. Well, I'm really delighted to see Professor Vijay Singh. I met Professor Vijay Singh almost 10 years back. Sir, namaskar. And really, it's a pleasure.
Thank you, sir. Thank you.
To teach science for all of us, particularly the physics, how to make it simple and illustrative. It's like art, okay? And when you like to listen to a great researcher and a passionate teacher who has taken the IPT in a long way from last decade. And well, we are eager because I listened to Professor Vijay Singh in a couple of events, and the way he brings down the things in audience is a great. Recently, I heard
Guide person, the voice or video is not clear. Please, Sapla ma'am, come on the.
What is it?
स्पीच का आप म्यूट रखिए, जो मोबाइल से कर रहे हैं वो म्यूट रखें प्लीज, देन यू विल बी एबल टू लिसन. Okay, so without taking much time, I invite Professor Vijay Singh. Please share your thoughts, because what we feel that whatever we are teaching, the way we teach, it carries a great impression. Like demonstrate something which is happening. It's like art. We are performing in front of students, okay, to justify any phenomena. For example, quantum mechanics, you like to teach and describe a picture of electron dynamics or the uncertainty principle. The way we represent, that's just totally an art of a teacher. So I wish that I like to learn from you the way we are teaching through demonstrations, the scientific models. How can we make it so attractive that it becomes a piece of art, okay, which the student can start loving, okay? So I request Professor Vijay Singh to share with the audience his thoughts around the theme science and arts. It's a great to listen to you. Please.
Thank you. Thank you,
Yeah.
everybody. Thank you,
Please,
Rekha,
yeah.
for enabling this talk. Thank you, Sapnaji. And thanks to Professor Ahluwalia and Professor Yogesh Vijay for giving such a nice introduction to this presentation. Okay. Science education uh, basically means several things to several people. One is that when people teach, you can see that a good teacher is a consummate artist. What he does is he choreographs the talk. He tries to put a certain amount of drama and suspense and anticipation in the students, and also a very clear board work and very clear enunciation is required. So in a large measure, what he or she is doing is basically being a good artist. The topic that I would like to address today is more about research in science education, whether that can be called scientific or not. Okay. There is some debate about it. So in the introduction, I will present a viewpoint, and that viewpoint will be that it cannot be a science education research, notwithstanding the fact that we have institutions such as Homi Bhabha Center for Science Education, notwithstanding the fact that several of us do science education research, there are some arguments to be made that it is not a science. Okay. However, I will then present a lot more arguments on the other side, okay, as to why it is a science. So let me begin the talk. I'll share the screen. Okay, if you'll allow me, this takes about a minute or something. Okay. And if you can't see my screen, please holler and tell me that this is not clear. So here it is. Can you see the screen? Can you see my
Yes,
talk?
yes, sir.
Yes,
Yes,
it
sir.
is
Yes, sir.
visible.
Yes, we can.
Wonderful. Thank you very much. I just want to draw your attention to my email, physicssutra@gmail.com, and you can write to me if you would like to have a certain paper that I'll be referring to or a group of papers, or if you would like to communicate with me. The other is a YouTube where I have a few talks on basically physics and basically physics in terms of being an art, and that is on the YouTube channel. And the channel is called Physics Sutra Official. So let me continue. Okay. Since most of us are from IIPT, but I assume that there may be a few who may not be. I have to tell you that I am a member of the Indian Association of Physics Teachers, and that institution has been around since 1984. We have over 10,000 members. We are a democratic institution. We are a grassroots organization. We are a voluntary organization, and we have several flagship activities. One has been mentioned, that is the Innovation Hub, which Dr. Yogesh Vijay runs. Okay, and in a true sense, it is probably the largest grassroots NGO in India. Okay, science NGO. Okay. Okay. So the outline of the talk is as follows. There is an introduction, and in the introduction, I present some arguments for physics, for science education research not being a science. Then I present some techniques of science education research, such as concept inventory and misconception study, peer instruction, and there's something called demonstrate, derive, deduce. And this topic on nurturing talent, I will skip. Uh, and also, I will talk about how SER may inform and influence science policy, okay, including gender issues and how to empower school and college teachers. So it's basically what you see here is a three-way yin-yang symbol. Science merges into research and merges into education, and they're all together here, as you can see on the right-hand side, on the top right-hand side. Okay. The hero of this talk. The hero of this talk is the science teacher or a school teacher or a college teacher. He's the true hero here. And let me begin the talk by saying a bit of history about this whole thing. Okay. And there was basically a book written by C.P. Snow in 1959 in which he talked about the two cultures, art and science. Okay. And C.P. Snow, of course, being at Oxford University and a very well-renowned academician, was well-versed with both, I think, both science and with art. Okay. So here he has something, here I've shown you something like a literature thing by Shakespeare, Romeo and Juliet or Hamlet, okay? And that is one aspect, and that is people who focus on it probably don't understand the other one, which is the science, where there are lots of equations and diagrams, and then you can see a lot of things. So there are two cultures. One is the culture which pursues humanities, and then there's another culture which pursues science, and the twain shall not meet. To quote Rudyard Kipling, it's like east is east and west is west, and the twain shall not meet. This is similar. Science is science, humanities is humanities, and this twain shall not meet. Okay, that's what. And C.P. Snow has something very interesting to say about the second law of thermodynamics, and I quote him verbatim. He says, "A good many times I have been present at the gatherings of people who, by the standards of traditional culture, are thought highly educated, and who have, with considerable gusto, with considerable enthusiasm, been expressing their incredulity at the illiteracy standard of scientists." Okay, they start lamenting that scientists are very illiterate people, uncultured and uncouth. So once or twice I have been provoked and have asked them, the company, how many of them could describe the second law of thermodynamics. The response from the humanities community was cold. It was also negative. Yet I was asking something which is about the scientific equivalent of, have you read a work of Shakespeare? So it is these two cultures exist, and he lamented it, and this divide has actually grown more. Okay. So let me come to some science part of this. Okay. A little bit of history of science education research. Okay. In 1957, the Russians put the first artificial satellite into space. And they beat the Americans, who had no inkling about what was going to happen. I mean, they didn't know that the Russians were way ahead of them in the space race. So it, in a sense, jolted the American community, scientific community, out of its complacency. It sent a shockwave through them. It made them panic. There was a lot of breast beating. So what happened consequently is they looked at the Russian textbooks and the Russian teaching methods, and then a whole lot of books came. And if you are wondering where these books, science education books such as Halliday and Resnick for physics and Atkins for chemistry came, these were problem-solving textbooks which grew out of the Sputnik. I mean, out of this a desire to teach the American students or the students in the West how to do calculations, how to solve non-trivial problems, and not just taking F is equal to ma, and m is equal to 2 kilograms, and a is equal to 5 meters per second square, and calculating F. So real problem-solving techniques came to the fore post-Sputnik. But that is the mainstream. Now, what I would like to draw your attention to is there was a subculture which grew, which I would call science education research. You see it down here, I mean, somewhere here, science education research. And this was led by people such as Arnold Ahrens, Frederick Rife, Lawrence Viano in the US, in UK, and then people like Romer in the US. So this whole group, it was actually a subculture, started claiming that although you're teaching problem solving, students still don't understand science. And this was a very revolutionary thing to say. It was hard for people to accept this fact. They started pushing, saying that science teaching is not tamasha only. I mean, how well you teach. Science teaching is also not just problem-solving textbooks. Okay, science teaching is much deeper and much more. Okay, so the point is, why is science teaching not a science? Okay, so what are the arguments you can bring about? Okay, let us think. Okay, I would like to think along with you, and even if I don't finish the talk, I think the aim of the talk is to generate this debate. One is what I would call the argument from anthropology. See, when you would like to test a student, a group of students, on how much they have learned, the very process of testing is putting some stress on the student, and it is not actually testing the student in a natural environment. It is what I call the anthropological principle. When you go to study a tribe, so to say, the tribe starts behaving, thinking what you would like them to do. So if you are going to observe them as a white man or a white woman, as to how the tribe is going to behave, they will think, oh, maybe they want us to dance, so we'll dance. Maybe they want us to be happy, so that they can write that these are happy people. The same is true of, say, field biology. Field biology is a very delicate science. In field biology, you observe animals or you observe birds. But the birds are also observing you, and they are tailoring their behavior to how you are reacting, because you're a human being, and human being is the greatest predator. I mean, the most dangerous animal on earth is the human being, and they realize it. Okay. So field biology or testing a student is not actually bringing out the real knowledge of the student. Okay. It's something like the uncertainty principle. If you test something, you first disturb it, and therefore you don't test the original aspect of the student. The second reason why it cannot be a science is the issue of repeatability. Okay. If I test you once, so depending on that, you have learned a few things. If I test you again, you won't get the same result. And the third most powerful argument, I believe, in my opinion, against science, education research being a science, is what I call the existence of a large number of variables. I mean, a performance of a student or the knowledge of, say, a class of students, okay, it depends on many things. It depends on how good the teacher is, how good the textbook is, how bad the student is. If on that particular day the student has had a bad stomach ache or something, it depends on his social environment. It depends on his family environment. It depends on so many variables, and so large number of variables, and some of them are hidden variables. I don't know what, you don't even know how to quantify those variables, that you cannot make the science education research a science. Okay. So it will remain an art, and it all depends on how well you perform. And then you keep your fingers crossed and you hope that you have done the best. Okay. So these are the three arguments. The one of, how should I say, disturbing the system, non-repeatability, and there being a large number of variables. Okay. So as a counter to that, let me give you a few arguments against it. Why science education research is also a science. Okay. So here is something. I put the slide forward to you as science education research scientific. Okay. Certain conceptions, are universal. They are not like dependent on some idiosyncrasies of that society or something. One of them is right here. Motion is along the direction of a force. This is a universal misconception. Here is something moving in a circle. You see the arrow, the particle is moving in a circle. You would think the force is tangential as it moves, but the truth is the force is perpendicular. Okay. This conception that where you are pushed is where you will go, where the force is where the direction of motion will be, is a universal misconception. Okay. Here is something moving in a parabolic trajectory. Okay. Here is, you would think that the force is acting along this line, this red arrow that you see, or this red arrow that you see, but actually the force is downwards in both the cases because it's parabolic motion. So in a sense, this misconception, or conception or misconception, there are certain which are universal. And what you try to uncover in science education research is what are the universal conceptions or misconceptions. That is one thing. Okay, let me continue, right? There are certain misconceptions or conceptions which are very robust. Whatever you do, you don't get over it. Okay. For example, evolution is a climb up a ladder of progress, and organisms are always getting better. That is what you think. And so what you have on the left-hand side is what you think of this notion of evolution. You were first a plant, then a tadpole, then a fish, and then a human being. Wrong. Evolution is actually like a tree. There are many different species which grow simultaneously. Many different evolutionary trees keep continuing, and a few survive. Okay. So the point is, this is actually a very big misconception about evolution. But there is also another aspect about this. and it has to do with language. So when you do science education research, you actually have to worry about your language. Okay, भाषा से भी बहुत भ्रांति होती है. Okay, for example, you say something like alpha rays. Okay, now you think because it's a ray, it must be a ray of light, but it isn't. It's a particle. Okay, right? And that is because we are at fault. It's not that the student is at fault. You should not have used the word alpha rays at all, but we are using that. Or we use words such as reaction forces. So when action and reaction take place, what we think is a reaction will take place maybe a few nanoseconds or a few seconds after the action. Because naturally, if I give someone a blow, the person reacts only after that, not before that, or not simultaneously. Okay. The most celebrated misconception, I think, regarding language has to do with light. So when you are no more, you said the light in his eyes died. उनकी आंखों की रोशनी खत्म हो गई, आंखों से रोशनी मिट गई. It is to say that light is coming out of your eye and then it's addressing, hitting the object and you see the object. Okay, this is called the extra emission theory of light. For a very long time up to the 10th century, until Alhazen argued against it. And he said that if you did this, then even in the night, if light is coming out of your damn eye, then you should be able to see objects in the night. And also, if there are objects very far away and certain objects close by, as you open your eyes, I should be able to see my wife, and then I will see the distant stars. That is not it. I see everything simultaneously. So this was another great misconception. Okay. So there are conceptions which are robust. A third argument for science education research is you look for the historical development of the subject and you decide what are the concepts by which certain universal misconceptions are persistent. Okay. Throughout all cultures, you look throughout cultures. So for example, heat flows from a hotter to a colder body. This is called a caloric theory. The caloric theory then implies that heat is like a liquid. The liquid, a hot liquid is flowing into a cold body through the crevices of the cold body and making that cold body equally hot or equating the temperature. But that is not the case. It is not a liquid, actually. Okay. However, having said that, I have to tell you something very interesting about this year 2023. This particular year is the 200th, I mean, by the way, the 200th centenary, 200 years are over of the Carnot cycle. And when Carnot proposed his engine, okay, and it's a celebrated Gedanken or thought experiment, the Carnot engine and the Carnot efficiency and the Carnot cycle, okay, this Carnot himself believed in the caloric theory. So often, I mean, it is very interesting to note that you may have the wrong notion, but you can still get a good theory out of it. Okay. So as a science education research person, I look for these things. Okay. I look for what conceptions are universal, what conceptions are robust, and what conceptions have been there throughout history in different cultures. Okay. There is a certain reason and there is a certain argument to be made and somewhat persuasive that scientific education research is scientific. So having said this, let me go and tell you some of the techniques that people use to pursue science education research. Okay. So one of the celebrated techniques, okay, and I pause for a minute to ask, to see if there are any questions on this. I mean, if anybody would like to make a comment on what I've said so far. Okay.
Sir, you may
So-
proceed.
Yeah, go ahead.
Yeah, yes, you may proceed, sir.
Okay. Thank you very much. Is my voice clear? I'm making a check once again.
Yes, sir.
Yeah.
Perfect.
Yes, sir.
Okay. Thank you very much.
Good.
So let me
Audible.
continue. Okay. So the techniques that we use, I cannot exhaust all of them, but I can tell you a few that people use. Okay. One of them is the concept inventory. Okay. Now you might wonder what a concept inventory is. It is a set of multiple choice questions. Okay. Now, multiple choice questions that we have is a dime a dozen these days, because all tests are basically multiple choice tests. Either one choice is correct or several choices are correct. But this concept inventory is different from a standard multiple choice test. It is and I will give you examples to show how it is different. It is aimed at probing alternative conceptions. So we are interested in seeing what the alternative conception is, what is the wrong conception, and eliciting ill-suited reasoning patterns. Okay. And it is also a very good diagnostic tool and an assessment tool. And I've written about it in Physics News about, I would say, 12 years ago, and I can share this paper with you. Okay. But let me give you some examples of what a concept inventory is. Most popular one was called the force concept inventory. Okay. And this is, I'll give you a couple of examples to tell you what these are like. Okay. So read this problem. Okay. I'll pause for a minute so you can read it, and then I will read it with you. So what it basically says is there's a channel or there's a tube which is kept horizontally and it is frictionless. Okay. And there's a particle which enters it at P and exits at R. So I show it to you here. Okay. There is a particle that is moving through this circular channel, which is, although it looks vertical to you, but it's actually lying on the ground. Okay. It's horizontal. Okay. And the particle enters at P and it exits at R. So the question that is being asked is, when it exits at R, which is the path that it will take? Whether it will take the path A, or the path B, or the path C, or the path D. This is from one of the very first concept inventory that was invented, called the force concept inventory. Okay. And what it is basically testing is the following. Okay, it is testing your knowledge of Newton's first law, or it is testing your knowledge of inertia. As the particle exits R, the tangent to it is along the direction B, and as it leaves R, it is going to go straight. It's going to go in the direction B, according to the first law. And the alternative conceptions, which are more interesting, one of them is A. It proves the fact, which many students are prone to make this mistake. They think of the training model. There's a training model in their mind which says that the particle has gone around in a circle for a long time. And because it has gone around in a circle for a long time, it has to come around in a circle because it has been trained to go in the direction A. Okay, you go in a circular motion. Okay. So you can see two aspects of this question. It is not that I want to test your rote knowledge about Newton's law, but what I want to basically tell you is that there is no algebra in this. In fact, most of these concept inventory questions, good ones, will not have any algebra in it, or very few, just one simple step. There is no arithmetic. There is no arithmetic. There is no calculation here. By algebra, I mean there is no calculation in it. And it is only testing a concept. And it is actually trying to elicit and see how many students have this misconception that it will take the training model and the training path A, or it will take the centrifugal path C. Because people have this feeling that when I go around in a circle, I'm going pushed out. So when it comes out, it will go either in the direction C or D. B is going to be the less likely choice unless you have read too much of Newton's first law. Okay. So there's a concept that is tested. There's an alternative concept that is being tested, training and centrifugality. And as you can see, there's no algebraic step involved. There's no numerical step involved. Let me show you another one that we developed. This one was, but before that, I will have to tell you that this is from the force concept inventory, which was the very first concept inventory. Okay. And there's something else I want to share with you. It was developed by Hastings, who was a professor, Wells, who was a school teacher, and also Swackhammer, who is also a school teacher. So it's, as I said, the hero of this talk is a school teacher. Okay. And it has stimulated research-driven educational reforms in physics. Okay. And Hake has gone as far as says as strongly as this, that prior to the CI, concept inventory. The inventory prior to this was the dark ages of secondary physics education. I'll tell you how the CI is developed, and I will give you examples of this as I go along. You conceive of a area that you would like. Say, supposing I want to test rotational kinematics. Okay, so this is the area. I give it to a student. I also start thinking about it, and I want to develop a concept inventory along the lines of rotational dynamics. Okay, so I do two things. I do a literature survey, which means I look up 20 books, which means I look up 20 question papers, etc., to see what kind of questions are asked on this. But at the same time, I do a cognitive analysis. I try to think what are the cognitive pitfalls that are possible in thinking about rotational kinematics. So one thing would be a student would think that, okay, rotational kinematics is about circular motion. It's a very common misconception. Circle mein jayega, that is rotational kinematics. Okay? That is wrong. The second is you might try to think that rotational kinematics, because it is circular or round, or in some sense, round, it is periodic. Again, wrong. There's nothing, they need not necessarily be periodic. Okay. So that's another cognitive pitfall that you have, that student has. A third would be something like saying that, okay, because if it is rotational kinematics, a straight line motion will not have any rotational content. Again, wrong, and I will show it to you. Okay. And then what you do is you develop a concept inventory. You make another 15, 20 questions, multiple choice. The wrong answer in which this ball goes around in a circle. Okay. So you do this cognitive analysis. You are also very careful not to make it very heavily dependent on something like, how should I put it? Like you should not make it very heavily dependent on algebra. Okay. And then you take help from teachers once again. Who will help you do this? Okay. Not some big professor. It's basically your school teachers and the college teachers who teach will give you help in this. And your bad students will help you out. Okay. Develop tell you